Why are free body diagrams hard for calculating stress? Imagine trying to solve a puzzle where some pieces are hidden and others are floating around in different directions. That's what working with free body diagrams can feel like when calculating stress. These diagrams are essential tools in engineering, but they can be tricky to use correctly. The main reason is that they only show external forces acting on a part of a structure, not what's happening inside the material. Stress is how the material reacts internally to those external loads, so the diagram is just the starting point, not the full story. When you draw a free body diagram, you pick a small section or component of a larger structure. You then show all the external forces and moments acting on that part. But you don't include the internal forces within the material itself because those are what you want to find out. This makes the diagram simple to look at but not enough to understand the internal stress distribution. To figure out the stresses inside, you need to analyze how these external forces translate into internal reactions. That's where the difficulty begins. One challenge is forces don't always act straight up and down or side to side. They often come at angles, so you have to break them into components using vector math. This process of decomposing forces adds extra steps and room for errors. Especially in three-dimensional cases, forces can act in many directions, making the calculations more complex. If you miss or miscalculate one component, your entire stress analysis could be off. Another problem is that the free body diagram must include all relevant loads and boundary conditions. Missing a force or misrepresenting how a support is holding the structure can lead to wrong internal force calculations. For example, if you forget to include a torque or a lateral load on a mechanical shaft, your stress predictions will be inaccurate. This can cause engineers to underestimate the risk of failure or over-design a component, wasting resources. Calculating stress often involves more steps beyond just drawing the free body diagram. You might need to create shear force and bending moment diagrams, then use formulas that relate these internal forces to stresses. Each step requires careful attention to detail. Loads can change with time or position, making it even harder to get an accurate picture. If you don't account for these variations, your stress calculations won't be reliable. In real-world applications, a good free body diagram shows how loads transfer through a component and how it reacts. But it doesn't directly show the internal stresses or how they are distributed inside the material. To fully understand where failure might happen, you need to combine the free body diagram with other analysis tools like stress formulas and material properties. So, the reason free body diagrams are hard for calculating stress is because they only show external forces, not the internal stresses. Forces often act at angles, requiring decomposition into components. It's easy to miss or misrepresent loads, and additional steps are needed to turn external forces into internal stresses. Plus, variable loads make the process even more complicated. Understanding these challenges helps explain why sometimes products or machines break down unexpectedly. Mastering how to use free body diagrams correctly is key to predicting and preventing those failures.